Good morning and welcome all to today's webinar. I'm Aranza Zugalan, part of the editorial board of BuildUp. BuildUp is Europe's largest international portal of energy efficiency and renewable energy in buildings. It is a unique community that provides the opportunity to discuss, contribute, and collaborate with other experts in the field. BuildUp aims to bring together stakeholders working in the building sector to reap collective intelligence about energy reduction by encouraging knowledge exchange. Our editorial work is organized around a topic of the month, which allows us to go deeper into specific themes. Each month, several items are produced as overview and technical articles and infographics, but not exclusively. BuildUp also offers the opportunity to host webinars on all the topics related to energy efficiency. More recently, BuildUp has opened the opportunity to distinguished experts in the field to share their knowledge in front of our cameras in the BuildUp Expert Talks. BuildUp portal shares daily the most relevant events in the field of energy efficiency and renewable energy, but also participates actively in many European events around the year as EPB Center and RIVA Conference, Horizon 2020, Interreg, and Cost Actions events, Covenant of Mayors, and much more, with the aim of further disseminating the results and helping to create high-quality media content. BuildUp content is updated daily, reaching around 120 new items each month. But BuildUp is not only us. BuildUp is a community, and we invite you to be part of it. By becoming a member, you can contribute uploading your own content and promoting your own news, events, or publications. BuildUp will help you to reach a broader audience through our social media channels and newsletter. It is a pleasure to host today's webinar entitled Lightweight Switchable Smart Solutions for Energy-Saving Glass Facades, which is organized by the Switch to Save project. Audience is welcome to send their questions through the platform. These questions will be answered at the end of the presentations in a session moderated by Lenka Bakharova from AMIRES, to whom I leave the floor now. Thank you very much and enjoy.
Thank you very much, Arantxa, for the very nice introduction, and thank you once again to BuildUp for hosting our Switch to Save webinar. Once again, my name is Lenka Bakharova. I'm from the AMIRES company, and in the Switch to Save project, which is, let's say, the main organizer of today's webinar, I'm leading the part dedicated to dissemination. So it is my pleasure today to lead you through this 1.5 hours that we are having together. The agenda, let's say the draft one is available right now on the screen. So at the beginning, we'll start with the overview of the Switch to Save project so that you have an idea what actually we are doing in the project, who are the main partners, what is our main goal. Then we will continue with some of the technical achievements that we have already achieved during the last, let's say, 3 years that we are working together. And we'll show you one of our demonstration, which is right now, let's say, in place and running. Then there will be a possibility to hear about our architectural design competition that is open to young architects, and my colleague Sarah will tell you more about that. And in the end, we will finalize with, let's say, overview of what is actually impact of Switch to Save and the technologies that we are having in it. At the end, there will be a possibility to ask questions. As already said, you can post them through the chat and they will come to us and we will be able to answer them, hopefully, in the end. So thank you very much for those who are online. And we immediately start with our first talk. So I would like to invite the Switch to Save coordinator, Matthias Falland from Fraunhofer FEP, who will, let's say, give a talk on the Switch to Save overview. Matthias, he has a PhD in low temperature physics, and he's active in Fraunhofer FEP. He's a specialist in sputtering and plasma processes, and since 2018, Matthias is the head of the department for roll-to-roll technologies in Fraunhofer. So Matthias, the floor is yours.
Lenka, thank you very much for introducing me, and hello also from my side. Good morning to the audience, to the online audience. In this first talk, I want to give you an overview about the Switch to Save project. which we are presently running, and make you familiar with the contents and with the achievements which we have done so far. Just a second. Now it works. Okay, good. I want to start with this motivation slide, where you can find three statements about the present challenges in the building sector in Europe. First of all, we need to say that in Europe we have around about 40% of the total energy consumption which is going into the building sector, or which is consumed by the building sector every year as an average over the countries. If I go to the right side, if one can say that if we would improve that, because a lot of this energy is consumed by buildings which have already a certain age and are not the most modern ones in terms also of energy efficiency. If you would find a way to improve this on the broad range, we could save roughly 5% of the total primary energy consumption of the European Union, which would be a great achievement, of course, with the background of the present energy and climate change challenges. And if I look into the building and we look where exactly we can achieve such improvements, then the windows play a quite crucial role. It's an important part of the building envelope, and in modern architecture, one can also observe that the area of windows related to the total envelope of the buildings is increasing. And this is a quite sensitive part of the envelope, because it's basically through the windows, majorly through the windows, the energy is exchanged between the inside and the outside. So one can achieve really a lot if it's possible to optimize this in the best way. So this all in all is our motivation in order to start this and perform the Switch to Safe project, because it's especially targeting these challenges. Okay, this is an overview about some facts of our project. On the right side, you see the facts of the project itself. You see the program where we applied for. It's about energy integration, energy of smart materials in non-residential buildings. That's the title of the project. We have the total project duration is 48 months, 4 years, and we are now roughly at the moment that we passed the 3 years. And of course, this is a good opportunity to present our results and also reflect on what we can still achieve in the remaining months and where we are in the project. And it's also a great opportunity for us to present ourselves here in the Build Up seminar. And thank you for giving us the opportunity to do this here. On the right side, you see the main objectives of Switch to Safe, which have been written down more than 3 years ago. And of course, they are still valid for us, and a kind of indication in which way we need to go and what we want to achieve. The project is about developing components for retrofitting. So it's exactly targeting the challenges which I have outlined in my first slide. We want to achieve improved insulation property. We want to make it possible to integrate the components directly into windows and glass facades. And we want to achieve this with reasonable costs. Reasonable costs are, of course, related to other solutions and to state-of-the-art installations. So it's not that everything should be cheap, but it should be effective and reasonable compared to other solutions. So that's the aim, what we want to achieve. At the end, we want to have components ready for retrofitting. So this is a short introduction about the consortium, which is targeting exactly this one. So we are covering the entire value chain of such a research and development project. So starting from really the basics, from the materials. Of course, we don't start from zero here. All institutions have already pre-existing know-how, and in the project, it came about the improvement of that, making it more reliable, making it more effective. But that was really only the starting point of the project. The main core of the project was the development of components out of these materials, which are ready for building integration. And finally, and that's where the project is presently, we want to go into buildings in order to demonstrate really what we have achieved and measure the effect. So this is a little bit more in detail on what exactly these steps meant. At the beginning, we had to look into the material which we had. So it's about electrochromic and thermochromic materials. So both of them special classes of switchable coatings, which are already known in science for a lot of years. And these materials should be improved and then put down onto components which are really prone to be integrated into demonstrator buildings and components. So it was in both of these versions flexible material, either functional film or flexible glass. And out of these, we want to make components, which are in our case basically windows. And these windows are then demonstrated at various demonstrators, real buildings in different parts of Europe. Presently, we are here in the middle, no, not in the middle, but closer to the end of the project, and we are indeed at the core part. Because the outcome of the project will not be to have just 2 or 3 buildings which are equipped with these smart or new materials, but the outcome is really to have the components available in order to equip different new buildings and really distribute this over Europe after the end of the project. So I have already mentioned the 2 terms, electrochromic and thermochromic, which play a crucial role in our project. And now I want to shortly introduce you about the nature of these materials and what we can achieve with this. If you look into window technology development, that has already a pretty long history. The first windows have been installed by human beings around about 4,000 years ago. But for a very long time, energy efficiency was not the main issue, which was connected to the development of windows. So this changed in the 70s and in the 1970s in the course of the first oil crisis. And since then, saving energy in the building sector really became an issue. And the first answer, which was well developed since then, was the development of low E and solar control coatings in order to make windows more energy efficient than they had been before. And this can today more or less be regarded as a state of the art, even though, of course, also technological developments in this area are still possible. But there's a very long experience also in installing these coatings in real buildings. Then we have the development of the IQs, and today, if you look at the today development, it's really to improving these achievements by the introducing the add-on of smart coatings in to achieve smart windows. Smart windows means that the windows change their properties according to an external stimulus. So there are several kinds of smart coatings available today, responding to different kinds of stimuli. The most important ones are the four which are here in this picture. And in the Switch to Safe project, we are concentrating on two of them, on the electrochromic and on the thermochromic coatings. So let's start with explaining what an electrochromic coating or electrochromic window can achieve. First of all, the stimulus which is changing the optical properties is an electrical control signal, meaning that is something which really an operator, a man, an owner of a building can control, or a human installed control unit can give out this electrical signal. So that's something which can really change intentionally by the control software of the building. So if you look into these graphs, you see what you can achieve here. If the sun is shining, you have basically two parts of this solar illumination. That is first the visible light which is coming in, and apart from that you have also the near-infrared light, which is not seen by the human, but which nevertheless is transporting energy to the building and is converted to heat in the inside of the building. This situation you have here on both sides, and what you can do with electrochromic coating is that you can tune the properties of the windows, and so you can control how much of each of the components is coming through the window. You see that you have a bright state and a dark state, and in the dark state you reduce the income, especially the incoming visible light, to a very low portion, but you have also a considerable effect on the near-infrared light. So what you achieve here is a shading for the light itself, but also a shading for the transmitted radiation. This is reduced to around about only 1% of the original values, which is coming from the outside. One needs to say that here is only the radiation transfer considered. There's also a heat conduction component which is not considered in this presentation, but also plays a role if you want to make detailed considerations. But the picture is basically as I have shown here. In case of the thermochromic windows, you have not the possibility to control it by yourself, but the window is controlled by the external stimulus of the temperature, meaning that the window is changing the property by itself if the temperature of the window is changing. Here you have the same situation. You have an illumination from the outside consisting of the visible spectral range and the infrared spectral range. You have a bright and a cold state in which you have a reduction of both components, and you have a warm state in which you have the situation that the visible light is more or less unchanged compared to the cold state, but you have a reaction only in the near-infrared, meaning that the window is controlling the amount of heat which is in the near-infrared range by itself, but it's not changing the radiation in the visible spectral range. You don't see the change, but nevertheless the energy input is by itself is changed. So as I said, we have made a lot of material development at the beginning of the project, and here in this graph I want shortly to explain you the outcome, what we have achieved. Here on the left-hand side, you see the solar spectrum. So there's a small portion of UV, which we do not consider here. Then you see a lot of energy is transmitted by the sun in the visible spectral range. And then you have here the near-infrared spectral range, which is transmitting the heat, but it's not visible for human beings. As a state of the art, we can regard the static coatings, the low E and solar control coatings, which are already known since the 70s, as I had explained at the beginning. The intention of these kind of coatings is to keep the transmittance in the visible spectral range as high as possible. So you have a small reduction compared to a glass, which is this 100% value. You see that low E and solar control are reducing this a little bit, but the main part and a very considerable reduction of the transmitted energy is taking part in the near-infrared spectral range, in the solar control a little bit more than in the low E. So what these state-of-the-art coatings can do is they keep the window more or less completely transparent, but they block the infrared spectral range, and so they increase the efficiency of these windows. So as I have said, in case of the electrochromic and the thermochromic, you can modulate this. Electrochromic is capable of reducing the bright, transparent range, which is roughly corresponding to the state-of-the-art transparency, to a very low window value that's almost completely dark, which is of course preferential if the sun is very strongly shining outside. And in the same way, you have capable of reducing the near-infrared spectral range, and if you go to the dark, you have also a reduction which is comparable to the solar control. If it's bright, it's a little higher than the low E. So here you have also a switching possibility, but the main emphasis is here clearly on the visible spectral range. If you look into the thermochromic, it's complete opposite. Here you have, as I've already told you, no effect in the visible spectral range at all, so there's no change. It's behaving like a more or less tinted glass because the transmission is much lower than in the state-of-the-art coatings. But you have a switching opportunity in the near-infrared, so here you control only the invisible part of the spectral range. So that's how the windows are working. And now, how do we demonstrate this in the switch to safe? So we have different steps, and already at the very beginning of the project, and I would say in parallel to the material development, we already started with the demonstration, and in this case, of course, it was based on modeling different buildings and see how much can be theoretically achieved if we install the materials which had been developed in parallel by the partners. And we have distinguished two situations from the geographical point of view. We have made estimations in Athens, and we have made the same estimations in Stockholm, which of course have completely different climatic situations and also different requirements concerning heating and cooling. And I need to say that these model buildings, which had been assumed here, had been buildings with a very high percentage of window installation, which can be typical for non-residential buildings, which are the topic of Switch to Safe, but of course not all of them are like that. And in particular, also the demonstration sites, which we will introduce later, do not have such a high window percentage as the ones which had been assumed here. So that's really an extreme case, and shows the maximum which can be achieved with these kind of windows. And you see that in both cases, we have a considerable reduction what we can achieve here. In Athens, it's more than 60%, which you can use as primary, which you can save as primary energy reduction. And in the Stockholm case, you have also more than 30% what you can achieve. And the way how you can achieve this is really different here in both cases, because in Athens you are saving for cooling, and in Stockholm, of course, for heating. And due to the special properties, especially of the electrochromic film, you also need to consider the savings which you achieve in inside illumination, because the electrochromic coatings are capable of adjusting the incoming light in such a way that you need here only a minimum. So this all together and the high window percentage leads to these maximum values according to the modulation of the building. So of course, but this is theory. We are now going to practice. And in practice, it's of course the question how you measure that you have achieved something. And there was a web package in our project which made a very interesting approach. It not only measured the temperature inside, but the main property was the so-called predicted mean vote, which is something which is measuring the well-being of humans inside such a room. And this is influenced by various factors. A very important one is the so-called thermal comfort, which is not only the temperature, but also air velocity, the floor temperature, and the wall temperature is playing a role, also the humidity which you have inside, and still some other parameters. Then the indoor air quality is also measured. And of course, the energy consumption measurement is a crucial quantity which finally will decide whether we had been successful or not. And these buildings, these measurements are made in rooms, not only with a single sensor, but you have a real distribution of different sensors in order to have a very comprehensive view on this on all these properties, in order to have a reasonable outcome at the end of the project. So the approach, how to come to the results, there had been two different approaches inside the project. So the most important one, which was for the big demo sites, is to divide the demonstration part in 3 phases. In the middle is the installation of the switch to safe components. As I have already said, that's where we are presently. Before that, the web package already started with the pre-monitoring of the interior of the demo sites, meaning that over more than a year, these installations of the different sensors had been made in order to really monitor all the parameters in an initial state. Now we have the installations, and right after the installations, post-monitoring of the interior of the demo sites will start, and then the post and the pre time will be compared, and then the effect will be measured. So as you might see, this is a quite challenging schedule. Challenging, it's due to the fact that due to external circumstances, which you probably all can imagine, the installation is later than we had initially anticipated, and this we mitigated with 2 approaches. One is that the post-monitoring will stretch beyond the end of the project, and the other one is that wherever it's possible, we change the approach in such a way that we try to have twin demonstrations, meaning that we install such to say components, and then we keep other rooms, other areas, more or less identical areas in the original fashion, and then we have a parallel monitoring, which allows us to measure the effect in a shorter time. So if possible, where possible, we take this approach also, and so we have 2 approaches in parallel. And with this, we hope that until the end of the project, which will be in September, we will have already reasonable pre-results, and then the completed results we will get only after a certain time after the end of the project. So yeah, here it's where we are. So installation of the components is taking place, and here is where it's taking place. So we have two big demo sites, one in Sweden, one in Greece. So we have two completely different areas in Europe. Both of them are non-residential buildings. The Kronan building is an office building, and in Athens we have a hospital. These two big demo sites are complemented by various mock-up buildings. We have here two mock-up buildings on the right-hand side, which are in Athens in Greece. These are at the technical university there, and these mock-up buildings they are full of sensor inside, and they really allow a very comprehensive measurement of the effects of any installation. So these buildings are of course not built only for Switch to Safe, but also for other projects. But we are happy that we can use it and really test both the electrochromic and the thermochromic coatings in these buildings. And additionally to this, we have still installed in Dresden small mock-ups for measuring the effect of thermochromic roof elements. Here we will exploit the parallel approach, otherwise it would be impossible to get the result by the end of the project. So with the introduction of these demo sites is the right moment to give the floor to Gregor as the next speaker. And with this, I want to finish my talk. Thank you for your attention.
Thank you very much, Matthias, for this introduction into Switch to Safe. And I think you gave a very nice, let's say, intro into our next speaker, which is Gregor Gregard from Chromogenics. And Gregor or Chromogenics is really a very important partner in our project. Gregor personally is co-founder and product manager since January 2003. And he is a CTO since January 2015. So he has a master thesis, or he has a master thesis on electrochromics. He, before, let's say, starting Chromogenics, he used to work at the Department of Solid-State Physics of Ångström Laboratory. And there, actually, with 5 other researchers, they founded Chromogenics. And since then, he has been working mainly with material and product development at IP at Chromogenics. So Gregor, the floor is yours.
Thank you, Lenka. So I will start this presentation by, let's see here, by going through some, let's see if I can get this to work. Okay, maybe I need some help to get to the next slide, please. Yeah, okay. So I will start with going through some technical achievements that was done in this project before we were able to start with the demo installations. So, yeah, okay. So the first very important technical achievement I want to bring up here is an upscaling. So we have developed industrial processes for large area coatings on PET films. And on the picture to the left here, we can see the roll-to-roll coater that we have scaled up the processes in. And we have scaled up processes for tungsten oxide and nickel oxide. And those are the electrochromic materials we use. And to the right there, we can see rolls of tungsten oxide, 1.6 meters width. So this is really a very large width. We can produce windows that is sufficiently wide for most of all the, let's say, commercial aspects of smart windows. And then in this roll-to-roll machine, we put in a roll of PET films with more than 1 kilometer's length. So the length is really not an issue, it's just the width that has some limitations. But it's not very often that there is a need for wider glass than 1.5 meters. I'll continue to the next technical achievement that has been vital in this project. Matthias gave you a lot of information about the electrochromics and the importance of having a high light transmittance in the clear state. And one of the objectives in this project was to reach a visual light transmittance above 70%. And that we have managed to do. Actually, we are now at 75%, which gives a very good light transmittance and a good indoor light situation in the building. It is, of course, very, very important. And also, as I mentioned, we have scaled up the coatings so we can build very large insulated glass units. And also objectives in this project have been to improve the insulation. And there we have a very low U value of this IGUs that has been developed. 0.4. This gives a very, very good value. And we have also reduced the weight compared to a state-of-the-art insulated glass units by 30%. And that is for a triple glass IDU. And as you can see on the picture here is a insulated glass unit. The width is 1.5 meters and the length is, I think it's 4.2 meters. This is, I would say this is very close to the largest we can produce now, because there is a limitation in the autoclave, in the glass lamination. So we cannot really fit glass that is longer than I think maybe 4.3 meters or something like that. Yeah, another very, very important, let's say, achievement and the deliverable in this project was to develop a wireless control system. The demo buildings, they're already existing buildings, and we don't want to interfere too much with the building. So when you install the control system, we want to get rid of all, let's say, as much wires as possible, wires for power supply and also for communication. So we have developed this system. You can see on the picture here, there is a very small solar cell that is placed on the outside of the window. And it's through this cable, it's connected to the control unit that is placed on the inside. And it's charging this battery. So the battery is really supplying the energy to the window when you do the changing. And the electrochromic window only need power when you do the color change. So when going from clear to dark or vice versa. When it's in its dark or clear state or some intermediate state, it does not require any power to maintain that level. And on to the left here, you see this is a radio module, and we have developed this wireless communication then, so that you can have long-range communication, Z-Wave or Wi-Fi. Wi-Fi was especially demanded by the hospital in Greece, where we will start the installation sometime next year. But for the project in Uppsala, we use long-range communication. Let's see here. So for the building in Uppsala, the demo building there, we have produced 157 square meters of smart insulated glass units. And as I now will shortly will go into talking about more of the installation of these windows. And also prior, as also Matthias talked about, we had this pre-installation monitoring. Let's see here, if I come to the next slide. Yes. So we have this pre-monitoring of a lot of different data types, but I start here with maybe one of the most interesting ones, the energy consumption. And this is the energy consumption for heating, cooling, and electricity, what we see here. So the black line is the total energy consumption. You have the orange color here is heating, blue is cooling, and the gray line is electricity. So you can see this is for from December last year until November this year. You can see there is a cooling need. This is in Sweden then, so the cooling need is only during the summer month. This was a different situation in Athens, of course. The building has a total consumption of 76.7 kilowatt hours per square meter a year. So it will be very interesting to see how that is affected for next year after the installation. Let's see here again if I can get, yeah, okay, there it comes. But not only energy consumption has been monitored, we have also been looking at VOC. This is this graph here, CO2, temperature, humidity, illuminance, and presence. So when it comes to the interesting things here, I would say that the gases we don't expect to see much there, but the indoor temperature, the illuminance, and perhaps also presence can be changed after the installation, especially if you have spaces close to windows where you have a lot of sun. People tend to avoid those areas during the summer month. It will be very interesting to see if there is a difference now. We'll continue again. Yeah, okay, here. This is the data here has been collected by Vasakronan. So this is Sweden, the largest real estate owner in Sweden, and they have a very good software for both collecting and presenting data. So it's very easy to compare data from, let's say, from different sensors that may be located on in different rooms and floors, and also, of course, from different time periods. So what we're looking at here is temperature variations over 48 hours. And down here we have the luminance levels in also during 48 hours. This can be presented in many different ways. So that's a really good. See here, if I go to the next slide. Yes, now I'm going to talk a little bit about the actual installation that has been done by Facade Glass. And before the lamination, the installation, they had to modify the profiles. As you can see, the existing insulated glass units was just 2-pane IDUs, and now it's a triple-pane IDU. So they had to increase this distance a little bit. But apart from that, everything has went smoothly. And I'm going to show you some pictures of the actual installation. If I only can change the slide here. Yes. So today, actually last week, we have installed all the glass panes or the insulated glass units. This is a 6-store building. And as you can see here, the glass is delivered on racks like this and lifted into place by a crane. And the people doing it from the outside, it's going by this forklift here. Now, and as you can see, we have replaced 3 floors when this picture was taken. So the blue more in the bluish tone is the original windows. And what's going on now, right now, is that we are doing the installation this week of the control system. It will be very easy to do now that it's wireless, and the follow-up monitoring or post-installation monitoring is just about to be started, and it will be done in the same way as it was before in the pre-monitoring. And we will have an extra focus on the energy consumption, the indoor temperatures, of course, also luminance and presence. So this is what I wanted to present at this meeting. So thank you very much for your attention.
Thank you very much, Gregor, for this very nice overview of the work that Chromogenics achieved during the course of the project, and also on the really ongoing installation in the Uppsala building. So I hope this gave a good flavor on actually what we are working on directly in the project with some practical implications. And right now, our next presenter will be Sarah von Rompuy, and Sarah will be presenting, let's say, specific activity that we are running within the scope of Switch to Save, which is the architectural design competition. Sarah, she studied architecture in Ghent and monument conservation at the Raymond Lemaire International Center for Conservation at the Leuven University. She's the owner of E2Arc. She has more than 25 years of expertise in the design, development, and execution of building projects, with a special focus on energy efficient renovation and conservation. And in Switch to Save, she's leading the design competition preparation, and she's also, let's say, contributing to other activities which are really connected with her background as the architect. So, Sarah, the floor is yours.
Thank you, Lenka. A warm welcome, colleagues, architects, future architects, and all interested in an energy-efficient building sector. As told, I will present the Switch to Save architectural design competition. We are organizing this with E2Arc. E2Arc is a partner in the Switch to Save project. We are an international team of architects working in research on energy-efficient buildings and urban planning for future cities. You will have to help me for moving because it doesn't work. Next slide, please. Yes, thank you. We all know how inspiring large glass parts can be and always have been in a building. Here you see the Gare Maritime at the Tour and Taxi site in Brussels. These buildings were constructed as a railway depot in 1907, and they now have been renovated towards an energy neutral building. Where the original building had single glazing, the renovated Gare Maritime has triple insulating and smart dynamic glazing, and all this without touching heritage values. Next. With its many forms, types, and applications, glass can enhance the architectural value of a building. Large glass facades and roofs are now a major design element. Compared to opaque materials, glass is associated with increased heat gains and losses. Therefore, glazing selection plays a key role in determining a building's overall thermal performance. When using glass, as you see here, as such a dominant facade feature, the choice of the glass is key. In modern buildings, up to more than 60% of energy transfer through the building envelope is related to glazing components. The strategy. With careful consideration of the orientation and the use of exterior shading, as you can see here in this building in Ghent, the integration of large transparent facade and roof elements can become an integral part of an energy saving strategy. Here you see that the window blinds are used to control the solar radiation, but as you can see on the photo on the right, these window blinds, they compromise interior daylight conditions and block the view somehow to the exterior. Here the architects have made the choice to make this is the architecture, the window blinds make the architecture. Another answer to these challenges can be what we present here, a high performance glazing. This glazing can contribute to the insulation of a building and deliver energy savings while ensuring comfort conditions for users and without losing sight and architectural freedom. Why would we use smart and switchable glazing? 1. Glass has no limitations, which gives more architectural freedom. 2. The electrochromic technology in the dynamic solar control glass stops the solar heat even before it enters the building. 3. It can act as an automatic climate system where unwanted solar heat radiation decreases, which keeps the premises cool, and the use of external solar control can be avoided. As a result, smart and switchable glazing can be very cost effective for our buildings. How does it work? How switchable smart glazing works, we see here also in the same building in Brussels, the Gare Maritime. How the properties of the glass parts change. Here it renders from clear to tinted in only 3 minutes. In only these 3 minutes, the complete transition takes place from transparent to a non-transparent surface, letting only 3% of the light through. 3 benefits of the automated dimmable electrochromic solar control glazing were of crucial importance here for the real estate developer Extensa. 1, its ease of use. 2, the avoidance of disruptive solar control elements on the historic facade, as well as its integration within the circular economy concept. In Switch to Save, within this project, we are developing this new and switchable window suitable for direct integration into windows and glass facades. Here you can see how smart the glass is and how it renders from very clear to very tinted. In this case, more and more tinted blue. On the window detail here, you see the triple insulated glass unit with electrochromic and thermochromic film laminated on the glass. The specification sheet will be soon available on the website. It will look like this, produced by Chromogenics. Now to the competition. We would like to promote what we are doing in the Switch to Save project by organizing this competition. It aims to collect design concepts of non-residential buildings. These can be new or innovation projects featuring glass facades, roofs, or large window-to-wall areas. We ask for a design concept. It should be non-residential, no other restriction regarding the size, location, or use of the proposed building concept. The project can be set within any hypothetical site or any size, anywhere in Europe, in the city, on the countrysides, in any climate. Who is eligible for this competition? The competition is open to students, young architects up to 10 years after graduation, alone or in a multidisciplinary team, up to 3 members per team, open to all nationalities. The team members should be based in the European Union or associated countries. The evaluation criteria. The design concept and the level of innovation. First one, we ask to elaborate on the design concept, the drivers, the possible barriers, other parameters like aesthetic integration, leading to the proposed design as a response to the competition brief. We also ask to describe the innovative aspects in the project regarding the integration of the smart glazing. The energy saving concept. Second criterion, describe how your project addresses the need for energy efficiency in view of the EU energy targets, how the design maximizes the energy saving potential. 3, the exploitation of the Switch to Save smart functionalities and the replicability. Describe how these smart functionalities have been integrated in your project across different design principles. Explain also how your approach in integrating the IGUs in your projects can be replicated in other contexts or has the potential to be upscaled. 4, the user comfort. Describe how your project is considering buildings, users' comfort, thermal and visual comfort, user controls, etc. The jury. The jury is a mix of people from academia and people from practice or industry. You can find the CVs on the website. The 6 person in a nutshell, I will describe them. Matthias Veland from Fraunhofer is a physicist and coordinator of the Switch to Safe project. Maria Faunti is an engineer and professor in the School of Mechanical Engineering of the National Technical University of Athens. Sarah Marompa, me, I'm a Belgian architect with both experience in architectural practice and research. Alexander Kraft has a background in electrochemistry and is an expert in electrochromic systems for Comogemics in Sweden. Hans Svart is an engineer, quality manager for facade glass in Sweden too. And finally, John Valtijk, he's the physicist and the CEO of Cat Market Limited Company. He is the former coordinator of the project and he's now member of the external advisory board. The prizes you can win: first prize €1,000, second prize 500. The winners will also receive a demo kit of a fully functional energy smart window, switch to safe window. They have the possibility to present the winning projects during the prize ceremony. The travel expenses will be covered and this will take place in Athens in the month of September 23. Also, a very interesting internship will be offered at the National Technical University of Athens for 6 months. And of course, there will be publication at EU-wide channels. What do we ask to submit? One PDF file, maximum 30 megabytes, with the brief description. You have the template, you can see it on the right of the competition brief. We are asking for one infographic presenting the proposed design in response to the competition brief and maybe other visual material. And then we ask to sign the declaration of ownership. How to submit? You have to register through a link. You find it on the website. After that, you get the confirmation of registration by email. The team leader gets it, so the team can be maximum 3 persons, with all the information on how to upload the proposal, the design proposal. You submit then your proposal to the own cloud. Then you will get the confirmation and the final results finally will also be communicated by email. The schedule, we have launched this competition in October 22. The registration deadline is end of January 23. We are open to questions till the end of February. We ask you to submit before the end of March and the winners will be announced the 16th of May. I thank you. And we hope that many students and young architects will take this opportunity to submit the design concept. Thank you very much.
Thank you very much, Sarah, for presenting the rule and the overall background of our Switch to Safe architectural design competition. And as you said, we hope that there will be many applications and we will be able to see what thoughts are young people having on how to use, let's say, the developments that we made in Switch to Safe. So thank you once again. And we are coming to our last presentation. And this one will actually summarize impact of Switch to Safe. And we go back to Matthias Veland, the Switch to Safe coordinator. So Matthias, the floor is yours.
Thank you, Lenka. In this presentation, I want to review the impact of the project. The impact portion, as you all know, is a very important part of every proposal and every project. And now, after 68 out of 48 months, we think it's time to look at what we have achieved and what we still can achieve until the end. So I want to start with this slide, which I have already shown at the beginning of in my first presentation. So we are here in the component, the completion, some of the examples how we do this and what we achieved have been demonstrated by or shown by Gregor in his presentation. So you have an understanding of what we do here. And for the impact, the two demo sites by themselves are important but not crucial. So we will demonstrate what we want to have achieved there and how we can save energy and how we can increase the well-being of the persons working there. But the main impact needs to come from the components themselves. They should be ready for renovations in Europe. And if we revisit the impact, then we revisit exactly this part, which is here highlighted by the red square. So let's have a look what was written in the proposal, so what's the project is about and what are the aims in terms of the impact. Of course, we have here various parameters. The most important one, and maybe, is of course energy saving potential of these components. But apart from this, there are also various other things which have been a part of the impact or had been important for the impact. The cost should be reasonable, and also preventing glare, fading, and overheating. Eliminate the need of shades and blinds. So Sarah has explained how important this can be for a historical building. Gregor has had made a remark about the presence of people inside such a room, which is equipped with a smart coding. Those are some social aspects for this as well. But the most important one is this energy saving, of course. So if you look into these impacts which had been described in the proposal, then we can say, okay, most of them are either met or we have a good chance to prove them in the remaining project time. So we are quite positive in what we have achieved so far in the project, and that we can bring this to a successful end. Nevertheless, I want to have a little more detailed look into what we actually have achieved and how this impact can be more closely examined. I want to start with these key results, which we had to transfer to the European Commission a couple of months ago in the course of our review meeting. So these are the four things which we have achieved so far, which had been as our main results of the project. So these are related to different aspects of the project. The first two are related to the smart coding components, the roll-to-roll made thermochromic systems. That's something which is really new and a very great achievement, has not done so far before. The second one is related to the electrochromic system, where such a roll-to-roll made approach is already realized for a couple of years. But here we have a very high performance in terms of visual light transmittance, as it was already outlined by Gregor. Also a great achievement, which is boosting the visibility of this component as well. To connect it to this, a fully wireless, controllable, lightweight smart IGU, which is an important thing if it comes to the installation of the components in a real building from the practical point of view. And we have these testing procedures, monitoring procedures, which are not only covering energetic parameters, as one might expect, but also the various other parameters related to the comfort of humans working in the rooms which are equipped with these components. So it's a more broader way, also taking into account social aspects of these installations. Also in the project, there had been various key performance parameters related to different components. Here, most of them are simply in black. That means they are achieved or slightly overachieved. There are some in red, which are where we are a little behind to what had been aimed for in the proposal, but nevertheless quite close. So that's not a very important issue that we are something behind here. But here's also a clear over performance in the VLT value which had been achieved. So all in all, one can say that the key performance parameters are also fulfilled. So from the project point of view and from the reporting point of view, I think we will be quite fine with this project. Nevertheless, I want to revisit some concerns which are generally connected to the application of smart windows. So this is something which is not completely new. So smart coatings, the basics have been already developed for quite a couple of years, and there are always sometimes discussions going on about the real use and the applicability and the potential for widespread use of these kind of components. And I want to discuss these concerns and somehow comment on how the switch to safe response to these concerns are. So the first one is electrochromic windows are too expensive. That's something which quite often is used, and anybody who has ever asked for a quote for an electrochromic window will see that this is of course more expensive than state-of-the-art low-E or solar control coatings. So that's true, and even though the cost aspect was somehow covered in the project as well, that's of course something which we cannot run away completely. So the question or the answer to this from the switch to safe point of view is, okay, the cost is higher compared to a static window. However, you have a certain advantage from that, and over a certain time, you will have an energy payback, which will, on the longer run or on the mid-term run, will lead to a saving potential in energy, and this is of course helping the general estimation of costs. As I've already mentioned, and Gregor has mentioned, we have overperformed in especially in the electrochromic windows. You see again the spectra of the two modi, the dark and the state and the bright state. So everything in between can be adapted. This is a real tool to save energy. How much can be saved? That's of course depending on the building and on the geographical location. And inside Switch to Safe, we have also developed tools to model this and make reasonable predictions. And with these two components, I think we can really give also a cost and analysis and somehow mitigate the concern that electrochromic windows are expensive. I want to move. Here I am. Okay, next one, installation of electrochromic windows are too expensive. Here it's about not the window itself, but on the installation. And it's related to the fact that you have to make a lot of wiring in order to connect each of the window to an electrical control unit. And everybody who did already installations in Windows knows that this can be also cost effective in the building phase. Here, the answer of Switch to Safe and especially of Chromogenics is to have this installing these self-sufficient control units inside the frame of such a window. You see here the control unit itself and how it's integrated in the frame. And you see the solar cells on the left-hand side as they are integrated in the frame. And as Gregor has mentioned, this can be used in several ways. You have different kinds of communication between these windows and control system of the building. And this together, of course, saves the necessity to have a direct wiring, which can be cost intensive and also cumbersome during the installation of the building. So I think these two major concerns for electrochromic windows we have at least addressed, and I think addressed also in a very good way. We have provided good solutions. Whether they are convincing or not, that's of course at the end of the day depending on the installations, on the special installations, and of what people expect. How about thermochromic windows? Thermochromic windows have a low light transmittance. Of course, that's true. That's something which we have already mentioned when I introduced the principle at the beginning. The light transmission is lower than the low E-solar control, and Gregor has also outlined that this is something which plays an important role for his electrochromic windows to have the potential to be as high as possible. And there's still another optical disadvantage of the thermochromic windows, that's the unbeneficial color. If you look into the color which is coming out of these transmission spectra, then you will see that it's yellow, which is not something which architects like, and most people don't like either. So how do we tackle this one? So we cannot change the world here, of course. So the material part has made some improvements, but finally we cannot run out of the general principles. But we have thought about the application scenario. And here we found out that for thermochromic windows, it's probably more efficient to put them into roofs instead of the windows, because both the light transmittance and the appearance of color is less important in these cases. At least it has the potential to do this. And it's also more efficient for thermochromic coatings to not to keep the warm inside the room, but keep the room cool when the outside temperature is changing. And you see the principle how this can work. So it's in the warm state, you block the light which is coming from the top. And in the cold state, you have a possibility of thermal radiation to the upper atmosphere, which is both of the scenarios are helping for a cooling system to keep the inside in a reasonable cool temperature compared to the outside. So these two concerns are considered by a slightly changed application scenario than we had anticipated it at the beginning. So the transparent roofs that become a little bit more important for thermochromics compared to the windows. There are two things still remaining. Thermochromic windows are unbeneficial, have an unbeneficial transition temperature. The temperature when the two states are the switching between the two states, and they have also a large hysteresis. So Sarah has shown that electrochromic windows can be quite fast within 3 minutes. Here you have this transition temperature, which is inherently you have only a very slow transition from one state to the other one, because the outside temperature is also not changing within 3 minutes, at least in most cases. So here I have, this is a slide I wanted to go. So here you see such a hysteresis. You see that if you look into the temperatures here, you see that it's indeed stretching over a quite wide range of temperatures, more than 40 Kelvin altogether, where you have this gradual change, and it's also you have also hysteresis, so it makes a difference whether you come from low temperatures to high temperatures or vice versa. And what we have also looked into is also temperatures in one of our demo sites. Here this is Athens. These are the temperatures in Athens over an entire year. And you see that you have a day-night modulation and you have a seasonal modulation. And if you have here an Athens summer modulation, you see where the summer temperatures in Athens are and how they are modulated in day and night. And you see that for the summertime you are exactly in the right slope here of this hysteresis. And in the winter time it's not as effective, but nevertheless you still have an effect. So that's a very special location here and a very special hysteresis. So one of our main tasks is to adapt the hysteresis to the optimum situation, and this optimum situation really changes from the geographical location. So the main thing which we are working on in the moment, also from the material point of view, is to realize a situation where we can deliver some comic coatings in the property on demand approach, so that we really have the optimum curve for a special application scenario, and especially for a geographic for a special geographic location. And optimum condition means that you can exploit both the day-night modulation and the seasonal modulation. So these are, again, all the responses of Switch to Safe to the concerns which are, of course, not told us, even not told us by our reviewers, but which are frequently discussed in any events or conferences where these kind of coatings and the usage is discussed. And now some comments about the TRL levels, which we have achieved in the project and where we are. Electrochromic coatings have already a TRL9 level in their standard setup. So you have seen some buildings where everything is already realized. So you have this. However, we have made, as I mentioned, some material improvements, and these are now in the demo site, so they are clearly not TRL9. We have judged this as TRL7 presently, and we want to achieve this monitoring in the next years, because the installations, of course, will remain where they are. We will achieve by this also then the higher TRL levels, but the new things obviously not TRL9 yet. The same is concerning the best properties which we have achieved, which is a combining of different technologies. Here we are still at TRL6, because it's not going into the real big buildings so far. And the same is for the summer comic coatings, where we have smaller mock-ups where we test the technology in the moment. So that's what will be the TRL level at the end of the project, which is, I think, not bad, but still needs some development, whether it can, until the point where it can really have a large impact on Europe, on the European building sector. That can still take some time also after the end of the project. So then another question is, what is more important, cooling or heating? You have seen the presentation some pre-monitoring times where both can play a role. The question is, what is more important? It's primarily dependent on the geographic location. So we have, if we distinguish predominantly cold climate and some intermediate states, and then predominantly warm climate, then there are different impacts of cooling and heating on the total energy consumption. And two of these geographic locations are covered by Switch to Safe. One is cold climate. This is what I see in Stockholm, and moderate climate with majority of warm days. That's South Europe, please. And both of them are topic in Switch to Safe. The other one is in the middle, of course. And real southern areas like in the desert also, that's not covered here. But if I look into the importance of the electrochromic and thermochromic coatings, then I see that the warmer it is, then the more important it can be. So that's definitely true for the thermochromic coatings, and for the electrochromic coatings, that's still a little bit under investigation. But you have seen that the main effect of the electrochromic coating is a shading without the use of curtains. And the shading, of course, is more necessary in areas where you have a very strong sunshine than compared to those where you have only moderate light. So that's why I would expect that also for the electrochromic coatings, you have more important, you can have a higher impact of the energy saving if it's coming about cooling. And sometimes it's too sensitive. Here I want to be. Okay. And what's the situation here? And here in Europe and beyond Europe today? Today we have in residential buildings, which had not been part of the Switch to Safe project, but nevertheless are important for the building sector. In Europe, we have only a negligible part which is going to cooling. Most of the energy is going to heating in Europe. And in non-residential building, it's a little different, but still it's a kind of balance. You also you have some cooling, but it's not crucial in the European Union. If you look into the future, and this is a graph here also on the right-hand side, it's a prediction for the selling of air conditioning systems worldwide. If you look how this is in Europe, then you see that there's a projection that this is increasing. So cooling will become more important in Europe. But if you look into the other areas, especially in areas like China or India, and you could put here still some other countries like Indonesia, for instance, then you see that worldwide for cooling, there's a very, very large increase expected in the next decades. And in Europe and in the United States and all Korea, that is, of course, driven by the global warming. But in the other countries, you still have an increase of welfare and combined with global warming. So, and this is why this is so important globally to have efficient cooling situations. That if you see that the smart coatings which we have developed here are especially well suited for saving energy in areas where you need cooling, that again emphasizes how important the results and the progress in this area is. So with this, I almost want to conclude, but for the impact, it is also very important that we network with other projects which are run in parallel, also on building envelope. So they are not primarily on Windows, but on the envelope as a whole. It is of course very good if we can cooperate with them for future developments to combine the solutions. So there had been a meeting at the Sustainable Places conference this year, and there the networking started and it's continuing. And we will think that by the end of the project we can present a combined solution which can be uptaken by other projects or by practice already, depending on how far we can go with this. In the summary, I would say Switch to Safe has fulfilled or will fulfill its goals by the end of the project. We will have the window components, and we will have also demo sites which can demonstrate them. What is needed is I would like the idea of having more funding also by the European Commission, also for bringing up the TRL levels of the most efficient solutions. We have seen that some of them are only at the TRL 6 or 7. And with having this in mind, it's of course good to have projects or calls which are addressing this and not only addressing demo sites. That would be one wish. And the other thing is extend the view beyond Europe. So the solutions which we have developed here are important for Europe, and they can achieve the goals which I have set at the very beginning. But if we are capable to bring them into action also outside Europe, especially in the southern countries in Africa or in Asia, then the effect for the climate finally can be even higher than if we concentrate only on Europe itself. And here I want to conclude with this, again, with this motivation slide, which I have started at the beginning also. Here again are the 3 statements, and I think finally that switch to safe can contribute something into bringing better solutions into action for tackling these issues which are written here. With this, I want to conclude. And again, thank you for your attention, for listening. And I think now we are open for questions.
Thank you very much, Matthias, for the summarizing presentation and let's say for showing the potential impacts of switch to safe and what could be the steps, let's say, to be done. And as you said correctly, we are right now have, I would say, 5-6 minutes for some question and answers. We have interesting questions from the online participants, so I'll start with them. There is a question for Gregor, which is saying that it was presented a case study where some modifications were needed in the facade to make it suitable. Do you foresee that this system could be implemented also in other renovation projects?
Yes, definitely. Definitely. Renovation projects are, I would say, that's the fastest, and now with the control system that is being wireless, I think this is a lot easier than it has ever been before. So definitely, yes.
Super. And there is also a follow-up question that was for Matthias, but I think you are the better to answer it. And it is, what is actually the longevity of the electrochromic glass?
I think there was some slides shown by Matthias,
Okay.
25 years of durability or lifetime. And we test it according to a test procedure that has also been developed in this project. And there we have 6,000 cycles in a very accelerated way of cycling, high temperature, fast cycling, deep coloring, and high voltages to accelerate the aging. So yeah, 20 years the expected lifetime.
Super. And last question for you. This would be what are actually specific advantages of having the electrochromic on foil rather than on glass?
That is actually also related to one of the things that Matthias brought up as a main concern on electrochromics, is that it's a bit costly. It's more expensive than state-of-the-art low-E glass. But the way we want to do this is to scale up a roll-to-roll production, so you can produce a very large quantity of electrochromic film, and then you can cut to size and shape afterwards. If you go by glass the other way, then you have to know exactly the dimensions of each glass pane or each window pane that has to be produced for a specific project, let's say in, I don't know, in France or whatever. And then that has to be produced, and you have to make an insulated glass unit and ship it from Sweden to France. The way we want to do it is to produce electrochromic film. Today we cut it to shape in Uppsala, but this could be done also, let's say, in France in that example. And it could be laminated by a local glass processor. And then they build the insulated glass unit close to the end user. So by doing this, we save energy and transportation. And also we have one product, we just produce electrochromic foil, and that being cut to shape later on means that we can produce a larger quantity at a lower cost. So yeah, those are the main advantages, I would say.
Excellent. Thank you very much, Gregor, for your answers. There is also a question from the external audience to Sarah for the architectural design competition. How far do the participants need to go into the facade techniques if they would like to apply?
Not so far. I think it's enough to hand in the execution details, but we don't ask for energy modeling. So the design, the execution details, which you would give to a contractor, but nothing more.
Super. And another question, as an architect, why would you personally take part in the architectural design competition? What would be there for you?
Well, I think at the start of an architect's career, these are the chances young architects have to take. I mean, they have to see that they get published in magazines, newspaper, interviews, and one of the chances is, of course, also taking part in competitions. And there is an extra positive thing is that by taking part in this competition and maybe winning it, they can get an insight into EU research and innovation of buildings. Yes, that's it.
Super. Thank you very much, Sarah, for this. And we have also a question for Matthias. They are mentioned, Emily, who is asking the question, is saying that it's very interesting and pertinent. The emphasis is in the need of monitoring. How long was the pre and post monitoring on place?
The pre-monitoring was always in the range of a year. So of course it would be beneficial to have it still longer, but it's a question of the project duration, of course, that we cannot stretch it as long as you want to. So pre-monitoring is a year, which is covering the entire seasons in a special location. Now we have the installation. The post-monitoring to the end of the project itself will be less than a year, unfortunately, because project will end. But as I have mentioned, the installations are not for the project only, they will remain where they are. And so the post monitoring will be actually more than a year, or 10 years it may be, but the cut after 1 year will be quite important for us for the dissemination, the after project dissemination of Switch to Safe, because then we can make a direct comparison over the entire season of 1 year at least, before and after. So after these post monitoring, 1 year is an important date, but the time after will provide statistics, which are also important. And we have definitely planned to exchange the information and bring them to the dissemination for a longer term.
Super, thank you very much. And as we are really at the end, actually we are 2 minutes over still, there is I would say a last question to Matthias, and then we will close. So Matthias, do you have any specific ideas about follow-up Switch to Safe project?
Yes, of course, I'm dreaming of it. I have a follow-up. So the follow-up should cover both demo sites and material development now. So it's something similar to what we have already, but as you might guess, there are also questions open. We have seen the great demands of electro and great challenges and achievements in the electrochromic part. We want to further develop the technology in order to bring the best solutions to a TRL level where they can go also in large demo sites. So that's still one thing. On the thermochromic side, we also want to go into demo sites, and we want to further develop this property on demand approach. So I think for all the technologies we still have possibilities to develop, and it would be great if we could win a project where we can do this. So I can also encourage the European Commission to consider this in terms of calls and of course judging proposals.
Excellent, thank you very much. So as we are at the end of our webinar today, firstly, I would like to thank all the speakers for presenting what Switch to Safe is about. I would like to thank all our online audience also for posing their questions. And last but not least, definitely, I would like to thank Build Up for giving us the opportunity to present Switch to Safe, and we hope to have you all participating in our further events or taking part, for example, in our architectural design competition. So thank you very much. And with the Christmas season, let's say upcoming, I would like to wish you a very nice end of the year and hopefully all the best for the upcoming one. So thank you very much and have a nice day. Bye.
Thank you very much. Thank you very much, Lenka. Thank you very much to all of you.
Yeah, thank you.